Good morning, good afternoon, or good evening, wherever you are, and thank you for joining us today on Thursday, the 19th of October, for this AMETEK battery webinar. It's been about a year since we've done a webinar on batteries, so we thought we'd return to it. There's some information that we've gone over before, but there's some new information in here as well, so hopefully it'll be good for everybody who's watching. As always, if you can let me know if you can hear me, that's always a very good start for a webinar. So if you go over to the sidebar and click on chat and then type in whether you can hear me or not, that would be appreciated. And it'd also give us time for everybody else to join us. So just wait for that to come back. Thank you, everyone. You can hear me. Always a good start. So while everybody else is joining, I'll do the introductions. My name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solidstate Controls. I am located in the Stafford office for AMETEK in our training center, just south of, well, actually southwest of Houston. I've got 20 years, actually it's 22 years now, in the industrial UPS industry. I originally started off in the North Sea. If you can't tell by now from my accent, I'm actually from Scotland originally, and I worked in the North Sea for over 10 years, installing, commissioning, repairing many different types of UPSs on the offshore oil and gas platforms. Then I moved to America about 10 years ago, and worked with a third-party representative for about 5 years, and for the last 6 years, I've been with AMETEK Solidstate Controls. So as I mentioned, I've worked with all major UPS and charger manufacturers, so I know a fair bit about UPSs for my sins. There will be a lag of around 30 seconds between you hearing my voice and me seeing a question, and that's basically because we use Webinar Jam as our webinar platform, and they have to convert this signal into an iOS device signal, into an Android signal, and into a Windows signal. So there is some processing that goes on, and that takes around 15 to 30 seconds. So when I say something and you type in a question regarding the thing that I said, I'm not going to see it for about 15 to 30 seconds. So what we usually try and do is, if we can wait until the end of the webinar, then I will answer all the questions that have come in during the webinar. If I do see something that's pertinent to the webinar as I'm going through it, then I will try and answer it, but it can be quite difficult with that delay. The other question that is always asked is, will the webinar be recorded? And the answer to that question is yes. It gets automatically recorded by Webinar Jam. And as you have signed up for this webinar, you will receive a link automatically when the webinar has finished, where you can rewatch the webinar whenever you want. The problem with the Webinar Jam replay is that it is treated as a completely new webinar from the viewer's perspective. In other words, you press play and you can't rewind or fast forward it. It's as if the webinar is live again. And obviously, if you're rewatching it, you don't particularly want to do that. So what our fantastic marketing team does, and London has posted it in the chat bar already, is we convert the Webinar Jam video into an MP4 basically, and upload it to our YouTube channel, and then you can watch it on our YouTube channel, and you can fast forward, rewind, pause, mute, whatever you need to do to make it a bit more palatable for you second time round. So the link is in the chat bar. It takes about 24 hours for the marketing department to do that, so it should be available for you tomorrow. And last of all, depending on how much I speak, which is usually too much, the webinar should last around 1 hour. And obviously, it also depends on how many questions we get as well. Okay, so without further ado, we will move on. So the outcomes today, we hopefully understand the basics of a lead acid battery, and we are going to focus on lead acid batteries today. And there's two reasons for that. The first is we're in AMETEK Solidstate controls are in North America, and by far the most common battery in North America is the lead acid battery. And the second reason is because I'm not really an expert in any of the other technologies. I'm although I've worked with NiCad cells and I've worked with lithium-ion cells, I'm in no way an expert or claim to be knowledgeable in those cells. So I cannot give you a presentation on those ones. We are trying to arrange with a contractor we use for our battery class here at the Stafford office that he can maybe do a NiCad battery presentation. We're trying to work that out for the future, so stay tuned for that. The next learning outcome is understand the purpose of a battery in a backup power system. Then we're going to move on to battery sizing, and we'll go through a simple exercise on how to size a battery for a UPS. We will discuss common maintenance mistakes, and then we will discuss some common myths about batteries. So that's what we've got planned today. So here is the most basic form of a lead acid battery. So you can see on the left-hand side, the red is the anode. That's the positive part of the battery. And that's made up, and I'm going to try and keep it as simple as possible because I hate chemical equations and PbSO and Pb and H2SO4. That goes over my head, to be perfectly honest. So on the on the left, we have the red anode, which is a positive plate, which is lead dioxide. And on the right, we have the cathode, which is the negative plate, which is pure, in most cases, lead or pure lead. Okay. And then those two plates have to sit within a diluted sulfuric acid mixture, which is called electrolyte. So without electrolyte, the battery will not work. That is how the ions move between the plates and create electric current. So as you can see at the top there, if this battery was fully charged, you would measure approximately 2 volts on a fully charged cell that is open circuit, that is not on charge. And we'll get to this in a moment. Okay. And then what happens when you put a load on the lead acid cell is the sulfuric acid, the electrolyte, starts to get absorbed into the negative plate, the cathode, and it gets turned into lead sulfate. And, you know, a lot of people say, well, obviously, there's no such thing as perpetual motion or perpetual energy. So as the battery discharges, people say, well, where does the energy go? And the energy basically gets taken out of the electrolyte. The acid gets taken out of the electrolyte, and it gets absorbed into the negative plate as lead sulfate. And that lead sulfate is actually, it starts to create a barrier on the surface of the negative plate, which makes it harder for the lead to take more acid out of the electrolyte. And in truth, you know, if you measured the specific gravity of the electrolyte, which is how much, basically it's a way of measuring how much acid is in the water. Water is obviously a specific gravity of 1. And in most circumstances, the electrolyte solution in a battery has a specific gravity of about 1.215 to 1.25 in a wet cell battery. And if you monitored the electrolyte as the battery discharged, then you would see that the specific gravity of the electrolyte would start to go down because the acid from within the electrolyte solution is getting absorbed into the negative plate. So that is why the specific gravity goes down. So, and then 2 things happen as it gets to the end of discharge on a battery. The cathode, the negative plate, has a lead sulfate layer on it now, which makes it very difficult for it to use the electrolyte, and the electrolyte solution has a much lower specific gravity because all of that acid has been absorbed into the negative plate. And then when you recharge it, it's just basically the opposite. The lead sulfate on the negative plate is expelled from the negative plate back into the electrolyte solution, and we revert to having a fully functional electrolyte, and there's no lead sulfate or very little lead sulfate on the negative plate after we have recharged the battery. So hopefully that didn't confuse you too much, because I think I may have confused myself a little bit. But that is the most basic operation of a lead acid battery. So the next question is, what is this? So that was a cell that we just showed you. So the question is, what is this? And many people will say, oh, well, that's a battery. Some people will say it's a jar, it's a monoblock, it's this, that, or the next thing. So hopefully we can clarify a couple of the terminologies that are used in lead acid batteries. Okay, so this is actually a jar or a container or a monoblock. Okay, and there's actually what we call 3 cells, and you can see here there is a compartment there, and there's a compartment there, and there's a compartment there. Okay, and there is the positive and the negative for the first cell, there is the positive and the negative for the second cell, and there is the positive and the negative for the third cell. Now none of these connections on the top of this battery are electrically connected. What you would have to do in the field is you would have to connect this post to this post with a bus bar or a terminal link, and also this to this. Okay, and then you would have a positive cable going in there, you would have a negative cable coming out here, and this would be a 6-volt monoblock. Okay, with 3 cells inside it. And then what's this? Well, this is what we would call a battery string. It's where either you have many monoblocks or single cell blocks, which these are here, connected in series together to make a fully functional battery. And you can see here, this starts at number 1 and this finishes at number 12. And I know that these are 2-volt cells, so this is a 24-volt nominal battery string. Okay. And just to complicate things, if we do a close-up of this jar here, this is actually a 2-volt cell. So if we just look at this container here, it's a 2-volt cell, but we can count how many positive plates. So we have 1, 2, 3, 4, 5, 6, 7. We have 7 positive plates, and that means we have 8 negative plates. There's always one more negative plate than there is positive plates. But this is still classed as a cell because all of these are connected in parallel. If you followed the positive plate up, it would go onto this terminal bus bar here within the battery itself. And then all the negative plates are connected on the other side, which you can actually see on this battery. This is the negative terminals here. All the negative plates are connected there. So all these cells are connected in parallel. So this is still classed as a cell, although it does have 7 cells connected in parallel inside it, just to confuse things. And then on the left-hand side, we have 2 examples of what a vented lead acid cell, or a VLA, is. And basically, if you can see the electrolyte inside a lead acid cell, that makes it a vented lead acid cell. Okay, and on the right-hand side here, you can see many different versions of what a valve-regulated lead acid battery or a VRLA battery, valve-regulated lead acid battery, looks like. Now, bear in mind the chemical reaction in both of these batteries is identical. Okay, we have a positive lead plate and we have a negative lead plate, and there is a sulfuric acid electrolyte inside them. They are identical in their chemical makeup. It's just how the electrolyte is contained in these valve regulated cells that is different. So in the wet cells or the vented lead acid cells, it is a solution that is very similar to water. In a valve regulated lead acid cell, it's usually either in an absorbed glass mat, in other words, like a fiberglass type mat between the plates that absorbs the electrolyte, or it's in a gel solution. So in both circumstances, if you cut open one of those batteries, in theory, no electrolyte is supposed to leak out. Okay. So now we're going to talk about the voltages. Cells are always listed at a nominal voltage. So for a lead acid cell, the industry standard says that a lead acid nominal voltage is 2 volts per cell. Just as a side note, for a NiCad, it's 1.2 volts per cell. And for a lithium ion battery, it is approximately 3.6 volts per cell. But you must check the data sheet because it does change between manufacturer and type of lithium battery that you are working with. Okay. In the industrial UPS and switchgear world, which is pretty much the world that AMETEK Solidstate Controls lives in, the majority of batteries contain 60 cells of lead acid. So that would be a nominal string voltage of 120 volts DC. For a NiCad battery, that would be usually around 96 cells, and that would give you 115.2 volts nominal voltage. And the reason why they don't have more cells, like 100 cells, to make it up to more like 120 volts, similar to the lead acid battery, is because the boost charge of an NiCad is usually around 1.45 volts per cell. And for 96 cells, that takes that voltage up to 139.2 volts. And we'll explain in the next few slides why we can't really go above that. Okay. So that is the nominal voltage of those systems. So for a lead acid system, the float voltage is approximately 135 volts DC. And we'll go into some different manufacturers. And the float voltage is the voltage that we need to charge the batteries at, that overcomes all of the chemical losses within the battery and keeps them charged correctly without overcharging them. It's manufacturer specific, but as a general rule, for a 60 cell system, it is around about 135 volts DC. Equalized voltage is usually 2.33 volts per cell. So if you multiply that by 60, it comes out at 139.8 volts for equalize. And then the end of discharge voltage is usually stipulated as 105 volts DC in the industrial world. And that is 1.75 volts per cell times 60. Because in a lead acid battery, you don't want to let the voltage get below 1.6 volts per cell. Once you go below that level, you can start to do irreversible damage to the plates by over discharging, and the sulfation takes hold much more below that voltage. So all the manufacturers say do not discharge your lead acid battery below 1.6 volts per cell. So therefore, the DC voltage range that the load should be able to work at is approximately 105 to 140 volts DC. And that's what we're concerned about. When we have a battery installed in a system, that battery has to conform to the load circuits. And in this next slide, this is actually from the specifications for a GMSG circuit breaker. I think that's an Eaton breaker. I can't remember, but it's a switchgear tripping and closing breaker. And it's saying the nominal, if it's a nominal 125 volt system, and on a side note, I hate it when they use 125 volts as the nominal. That's actually 120 volts. 120 and 125 volts are interchangeable. I don't know where 125 came from, but 120 is the actual nominal voltage because it's 60 cells usually. But if you look in this column here, it's saying the voltage range to allow that breaker to close is 100 to 140 volts DC. Okay. And if you go into this next column here, for this particular type of breaker, to trip that breaker, the voltage must be between 70 and 140 volts DC. Okay, so this one here is what we have to conform to. So therefore, the DC from our battery and charging system cannot go above 140 volts and should not go below 100 volts to allow the closing of this breaker here. Okay. And for a UPS, this is the rating plate for one of our inverters, a 7.5 kVA inverter. And we stipulate that the DC input into that inverter must be between 105 and 140 volts DC for it to work correctly. Okay. So that is why we use 60 cells in lead acid, and why those voltage tolerances are there is because all the load circuits that are connected to the DC will have some form of tolerance that we have to adhere to. Okay. So on a side note, the open circuit voltage is the voltage of a fully charged lead acid cell after being off charged for a period greater than 24 hours. So basically, if you have a cell that has been disconnected from the charger and left for 24 hours, that cell is still fully charged, but we can actually get some information about the state of charge of that cell. And the equation is that the open circuit voltage should be the specific gravity number plus a value of 0.84. That's just an industry standard. So for many lead acid cells, 1.215 is a common specific gravity. If you go to many of the data sheets for many of the lead acid cells in the US, the specific gravity of that cell may be 1.215. So therefore, the open cell voltage of that type of cell should be 1.215 plus 0.84, which is equal to 2.055. So very close to the 2 volts nominal that we discussed. So we just wanted to prove to you that that's why we say a lead acid cell is a 2 volt nominal cell. And in truth, if you had a cell that had been off charge for 24 hours and the value that you measured, the open circuit or the open circuit voltage, was less than 2.055, then you can start to assume that there may be something wrong with that battery. Obviously, you would have to check the specific gravity of the electrolyte with a hydrometer to make sure that it is 1.215 before you add that 0.84 on. But if they don't match, then there is something wrong with that battery. Okay. So, you know, we've talked about 120 volts many times on this presentation already, but most of you will know that when you actually go to a battery that is on charge and you take a fluke or any other kind of multimeter and you go on the positive or the negative of the battery, you are going to see approximately 135 volts DC. Okay. And that as I mentioned earlier, is manufacturer specific, because we need to overcome the self-discharging chemical reaction of the battery. If you just left a battery fully charged in a warehouse at 77 degrees Fahrenheit, over a period of 6 months, that battery will start to internally self-discharge. And after 6 months, you would have to perform a charge on that battery. It's just inherently what happens because of the chemical reaction within the battery itself. So the battery manufacturer has done a lot of research, and they've worked out a voltage, a charge voltage, that does not overcharge or cause water in the cell to evaporate excessively, and it also overcomes the self-discharging chemical reaction of the battery. So that's what float charge means. You can leave it on float charge for pretty much forever, and you will only have to do minimal water replacement in that cell. That's the theory anyway. So I mentioned that it's manufacturer specific. So for Enesis, I just picked out, I can't remember which cell this was, but this was a specific type of Enesis cell. And if the specific gravity of the cell is 1.25, because they give two versions of this monoblock here. So if the specific gravity was 1.25, then it's saying also, if it's an antimony cell, which I'm not going to go into the difference, but basically it's the difference of the plate grid. The majority of plate grids, which is how the lead is pasted into the battery, the majority is calcium, but there are some out there that are antimony or low antimony, okay? But they're saying if it is a 1.25 specific gravity cell that has an antimony plate grid, then it's saying that the float voltage should actually be anywhere between 2.17 and 2.21. So in that circumstance, it should be about 2.19 volts per cell, okay? And if it was a 1.215 specific gravity, it should be between 2.15 and 2.20 for the antimony cell, which would be about 2.17 volts per cell, okay? And then for the calcium cell, which is by far the most common, for a 1.25 specific gravity is between 2.21 and 2.30, which is where we get 2.25 from. And if it was an antimony cell, if it was a 1.215 specific gravity, it would be between 2.17 and 2.26, which would be about 2.22 volts per cell, okay? And then if you had 60 volts in the string, you would multiply any of those values by 60 to get your float voltage, okay? So 60 times 2.25 is actually the common 135 that we say, but you can see for this high specific gravity antimony cell, it would be 60 times 2.19, which would be just short of 130 volts. Actually, no, let me do the calculation. It's not short of 130 volts. That's what iPhones are for. Everybody's shouting at me down the screen. 60 times 2.19 is actually 131.4. It's not that, it's 131.4. So you can see, there's nearly a 4 volt difference between those two. So you have to be clear that you have to check the manufacturer's guidelines before you set the float voltage on your system. And that's just for Enesis. So for C and D, you can see that the recommended float voltage for this particular type of cell is between 2.2 to 2.25 for calcium cells. So you would set it at 2.23 for a calcium cell. And if it's an antimony cell, C and D is saying it should be between 2.15 and 2.28. And that's a 13 difference. So it'd be 6. So it would be about 2.21 volts per cell. Okay. So that's C and D. And then for Hoppeky, they've basically listed each type of battery for you. Most of them are 2.23 volts per cell, but there is this one down here, which is the OSP.XC, is saying is 2.25 volts per cell. Okay, so all the manufacturers have different voltages that they recommend that their specific cells should be charged at. So why do we use batteries anyway? Well, because Westinghouse and Tesla won the battle. You can't store AC. All the AC in North America pretty much is generated as AC. All the power, should I say, is generated as AC using rotating machines, basically turbines, steam turbines, even nuclear power. It is they use the nuclear reactor to create steam. That steam then gets put through a turbine and spins a generator. Okay, and you can't store AC. If you do know how to store AC, please let me know, because I'm going to patent it and then make a huge amount of money. So the grid is good, but there will always be power outages. You know, the grid in the US is usually very reliable. But, you know, somebody in your local neighborhood, a big truck can run into a power pole, knock down part of the system, and you're going to lose power to your facility in some circumstances. So you cannot rule out that there will be power outages, sags, surges, or anything like that. So that's why we use batteries. The batteries' only purpose is to store electrical energy. So if there is a power outage, it is then therefore available to maintain the circuits connected. Okay. So it's very important that the only purpose a battery has in a UPS system or a DC system is usually to store the energy. Okay, like I said, in a UPS, its main purpose is to store power. So if we do lose AC input to the UPS, then the batteries will carry on supplying the inverter with the DC power that it needs to convert it back into AC. So therefore, we need to know how to size the batteries. You know, we need to know what battery to buy to get the time that we require for that particular system. So I'm only going to cover battery sizing for a UPS because we're a UPS company, and it's just what we do on a regular basis. So this is the rating plate for one of our 10 kVA DPPs. Okay, and it's saying that the DC input is 120 volts DC, so we know it's a 60 cell system. Okay. So we don't live in a perfect world. Okay. Inverters are not 100% efficient, and also a 10 kVA inverter with a 0.8 power factor. If we go back to the slide, you can see here it says it's a 10 kVA system, but it's a 0.8 power factor. So we can actually only put 8 kilowatts of real power out. Okay. So if we put all of that into our system, we are saying on the output of our inverter, we can only supply 8 kilowatts. Okay. But then our inverter is only 88% efficient. And I got that from the DPP spec sheet. So all the engineers should know from our spec sheet what the inverter efficiency should be. And ours is 88%. So therefore, you divide 8 kilowatts by 0.88, and you get this number here. You need 9.09 kilowatts DC power into the inverter to be able to overcome losses and put an 8 kilowatt output. Hopefully that's clear. So we need 9.09 kilowatts to generate 8 kilowatts of AC power. So now we know that. That allows us to work out the DC current required from the battery at full load. Now, remember, this is very, very important. We do expect the battery to discharge down to a voltage of 105 volts DC. That is the end of discharge voltage. So as current is inversely proportional to voltage when it comes to power, we have to make sure we use that value, because more current is going to be needed to give the same amount of power at this lower voltage. So Ohm's law states that P is equal to VI. So therefore the current is equal to the power divided by the voltage. So the current is equal to the power, which is 9.09 kilowatts, divided by that end of discharge voltage, 105 volts. And that comes out with, we will need, worst case scenario, 86.6 amps of DC power to maintain that 8 kilowatt load. Okay. The next question is, how long do we need that 86.6 amps? And that's down to the safety requirements that are put into the load at the design stage. Like, for example, a data center, a huge data center only needs a backup time of about 15 minutes because they're trying to power the UPS while the emergency generators get up to speed, and then the automatic transfer switch transfers back to the generator. But in a petrochemical plant or in a power station, we are doing it more for the safety requirements, where we either want the process to get into a safe mode of operation, or we want the tripping and closing supplies on a DC system to be able to trip and close for a considerable amount of time until the power comes back on again. So if there's any issues while the power is off, the DC can maintain it. So we're going to assume in our calculation that we need 3 hours of runtime, which is a pretty standard value for the petrochem industry. The last thing we need to do is decide which manufacturer and battery type. And this is up to you as the end user. We have no ties with any battery manufacturers. We will supply you with Enesys, C&D, Hopper Key, whatever. We don't care. I'm just more familiar with Enesys through all the work that I've done over the years. So I just stick with Enesys. It's in no way recommending Enesys to you. It's just something I'm more familiar with. So we're going to say we had a previous good experience with the DX range, and we would like to use them again. So we would go to the DX, the Enesys DX datasheet, and we would look up the table, and we'd find that for the 3 hour rate, we need a value above 86.6 amps. So the DX5 is not good enough. It's only going to give us 69 amps. But the DX7 will give us 99 amps, which is above 86.6. So that is good. So we can say, okay, the DX7 will fulfill our needs. It will do 3 hours at 86.6 amps. So we are good. So that's the easy way to do it, okay? So that's the hard way, should I say. The easy way is to get with Enesys. They have a software package, and basically you can type in all of that data, basically a 10 kVA UPS, power factor of 0.8, inverter efficiency of 0.88, number of cells is 60, and basically it does all the calculations for you, and it lists all of these suggestions that you could do. Okay, you could do 2 strings of ES05, 2 strings of the CX09, but like I said, we had good experience with the DX, and the first DX that shows up is the DX07, which is the one that we chose, and there's actually a margin of 20.3 on there, so it is a little bit oversized. And then, you know, you can make a decision on which cell to use here based on cost, if absolutely necessary as well. So that is how to size a battery. Now we're going to go over some maintenance mistakes. One of my pet peeves in maintenance mistakes is intercell resistance. Okay, it's a bit difficult to tell in this picture, but this is what the post should look like, a nice gray silvery color. You can see this post here has some lead dioxide on it. That's what this black stuff is. And that usually means that there is a jar cover leak or crack here that is allowing electrolyte to leak up from inside the battery and then up into this post, and it's putting a coating of lead dioxide. And that lead dioxide is very, very hard, and it has a high resistance. So in theory, if the surface of this post here to where the intercell connector is connected gets contaminated with lead dioxide and it creeps up and there isn't any grease or anything to prevent that, then it could lead to a high resistance connection. And that's why it's important whenever you're doing the intercell resistance of a battery that you have to go from the post. Okay, you have to put one connection of whether it's your DRLO, your low resistance ohmmeter, or your cell corder, because you want to monitor the current going through the post, up, then through this connection here onto the bus bar, along the bus bar, down back through the post, down onto the post again. Okay? You want to get post to post because then you are measuring this connection here and this connection here. Okay? In truth, we don't really care what the intercell resistance is of the copper bus bar, the tin coated copper bus bar. That's just what it is. That very rarely degrades. It is the intercell connection surface where the resistance can go up. So when I see people put their probes on like that when they're trying to test the resistance of a connection, that does absolutely nothing. That is not giving you any data whatsoever. It's just telling you what the resistance of that copper bus bar is. And that's going to stay the same no matter what. Okay? What you need to do, so here's another example. This is on a valve-regulated lead-acid battery. Many people would put their clamp on this here, or they may even go back onto the terminal barrel here, okay, to get the resistance. And that, once again, doesn't give you any information whatsoever. To get your clamp would have to go on this bottom post here and on the bottom post here, okay? And that clamp cannot touch this portion of the lug, because as soon as it touches that, you are not getting the surface connection resistance. And that's what we're trying to find out when we do intercell resistance measurements. Okay. And it's the same with these AMETEK cells. You must get your clamp. So let's say the clamp comes in this way here. It must go down onto this post and this post. Okay. It cannot touch this intercell bar, the connection bar. It must only touch the post because you have to get the surface connection resistance. That's what we're looking for. So that's my pet peeve for maintenance mistakes. The next one is my battery voltage is 135 volts DC. Therefore, my battery is good. Oh, how wrong can you be? The float voltage of your battery gives you absolutely no indication of the state of charge or health of your battery. Okay. And here's a good example why. So we have our 120 volts AC going into our house, and we have a circuit that has 3 lights in our house. Okay. And if you measure across each of these lamps in the fixture itself, you will measure 120 volts AC. They're all in parallel. Hopefully that makes sense. Okay. Basic light circuit. If we removed one lamp, let's say it's a screw bulb, we remove the bulb. If we still go on the fitting and measure at the terminals, we will still get 120 volts, even though there is no bulb there anymore. Okay, we still have 120 volts AC there. And the same applies to DC. If we have a 135 volt charger here, and we have 3 batteries in parallel, we are going to measure 135 volts DC across the positive and negative terminals of this battery. Okay? If we remove this battery completely, but we still measure at the terminals of the cables going to that battery, we will still measure 135 volts DC, even though there is no battery there. So how on earth are you going to figure out the state of charge of the battery? If you remove the battery, you still get 135 volts. That voltage is the voltage of the charger. Okay? That's all it is. It has nothing to do with the state of charge of the battery whatsoever. So if we didn't have 3 batteries in parallel, we just had 1 battery, we would measure 135 volts DC. If there was an internal problem, or if you remove that battery completely, 135 volts DC. If there was an open circuit cell in that battery, you would still measure 135 volts DC. The voltage of the battery does not tell you anything about the state of charge of that battery. Biggest maintenance mistake. Another maintenance mistake is people don't understand that stationary batteries are dangerous. Okay? You can see in this cell here, this is the electrolyte level here. Okay? So there is an area between here and here, between the top of the electrolyte and the top of the battery lid, that is full of hydrogen. And everybody knows that hydrogen is an extremely explosive gas. Okay? Now, in truth, there will be a flame arrestor on the top of the battery. And what the flame arrestor's job is if there is any ignition source outside of the battery, that if it does ignite, that cannot get back through the flame arrestor back into the hydrogen inside the battery and cause a huge explosion. That is if the flame arrestor is fitted and if the flame arrestor is correct. This is what can happen. Okay, this is at I can't remember where this is. This is at a warehouse where this whole battery string was being charged up. They'd probably been stored for 6 months and they were recharging it to maintain the charge. Okay, you can see first mistake. They left the shipping vent plugs in the battery when they were charging them. Okay, they should have taken these off and put the flame arrestors on when they were charging them. And then what happened was, after the recharge or during the recharge, one of their technicians was using this rag down here to wipe down the tops of the batteries, probably to remove most of that polystyrene that's on top of the batteries. Okay, and in doing so, he caused an electrostatic charge to build up when he was rubbing the side of these batteries. And because these vent plugs are not designed like a flame arrestor to stop the hydrogen igniting, some hydrogen did escape out of these vent plugs, and obviously this vent plug on this battery here, and it allowed that ignition source, that electrostatic discharge, to ignite the hydrogen that was probably sitting on top of the cell, and then to get down into the hydrogen space inside the cell, and it blew off the top of the battery. And obviously that's not a good day for anyone. Okay, so please bear in mind that hydrogen space is extremely dangerous. You have to be very observant when you are around batteries. Another maintenance mistake is, can I measure the battery voltage at the charger terminals? Okay, and the answer to that is it's no, you should not be doing that. Okay, in this circumstance, if we measured at the at the charger terminals, we would get 135 volts DC. These breakers are drawn open, but they are actually closed. Okay, And then this one here is closed. We would measure 135 volts DC. But this one here, the battery breaker, for some reason has been left open. So if you measured at the charger and said, okay, 135 volts, my battery's being charged okay, you're not getting the full facts, because if you go out to the battery, if this has been left off charge for a considerable amount of time, it could be 124 volts, it could be even lower, because you didn't know that this breaker here was open. Okay, so when you are measuring the voltage for your battery, always do it at the main positive and the main negative of the battery. It's the only place you should be doing it. I know sometimes the battery room is in a different location. It could be downstairs. It could be in a locked room. It doesn't matter. You have to test the voltage at the battery to make sure that the charge is getting there. Okay. I mean, basically, also, oh yeah, I know what the slide is saying. And also, if the battery room is in a different location, you have this cable here going to the DC panel, and then you have this cable here coming from the DC panel to the battery. That could be 200 feet. Could be more, it could be longer. So there could be some volt drop in that cable. Okay, so you could measure 135 volts DC at the battery, but at the charger, sorry, but if you go out to the battery, because of the volt drop in the cable, now it'd be unusual for it to be too much of a volt drop because there's a very small amount of current flowing through it, but it could go down to 133 volts. And that means if the manufacturer says that has to be charged at 135 volts, that battery would be undercharged. Okay. Another maintenance mistake is people don't realize that temperature affects the battery. Okay, the capacity of every lead acid battery is reduced by sulfation of the plates. Okay, that's how you lose capacity, is sulfation of the negative plates. So during prolonged periods of being undercharged, it could be months, weeks or months, not days, then the normally occurring lead sulfate converts to what's called a stable crystalline and deposits on the negative plates. And that leads to the development of large crystals that reduce the battery's active material and leads to low capacity. So basically, sulfation of the negative, sulfation of the plates causes low capacity inside a lead acid battery. Okay, so if you are undercharging a battery, then you are allowing the lead sulfate to build up. So this is from this bottom portion here is from a manufacturer, and it says, while on constant potential charge, the battery current will halve every 8 degrees Celsius or 15 degrees Fahrenheit. So what that's saying is, in the US, they say that you should charge your batteries at 77 degrees Fahrenheit. Okay. If your temperature went down 15 degrees to 62 degrees Fahrenheit and you didn't adjust the float voltage, then the battery current will halve, and therefore you won't be overcoming the internal chemical losses that are going on inside the battery, and the battery will start to discharge in sulfate slowly. Okay, so temperature, low temperature does affect the state of charge of the battery if you don't adjust the float voltage. And conversely, the life of a battery will halve for each 8 degrees or 15 degrees Fahrenheit. The battery temperature is above 77 degrees Fahrenheit. Now, that is over a prolonged period of time. So, we're not saying if the battery goes up to 100 degrees Fahrenheit for 2 days, that the battery life is halved. That's not what we're saying is, but if it is 100 degrees Fahrenheit constantly, then that will reduce the battery life by half. Actually, it's not even 100 degrees. It is 77 plus 15. So it would be 92 degrees Fahrenheit. You will lose half of the life of your battery. And then also what you've got to understand is, while on constant potential charge, the battery current will double every 15 degrees Fahrenheit. that you are above 77 degrees, okay? And for a valve regulated battery especially, that can result in thermal runaway. Because what happens in thermal runaway is if the current increases, then the heat inside the battery, there's more current than necessary going into the battery now. So that causes the battery to heat up. As the battery heats up, it takes more current. That more current causes the battery to heat up even further. And then it's a snowball effect that is called thermal runaway. And we couldn't find a really good picture of thermal runaway because usually the batteries are destroyed. But you can see quite clearly here, these valve-regulated lead-acid batteries have swollen a huge amount. And what happens is these were going into thermal runaway. The insides were heating up so much, causing pressure and causing the plastic to melt and the jars to expand. They were lucky in this circumstance because that was found before those batteries went on fire. And those batteries could have gone on fire if it was left too long. And now we'll go into battery myths. Replacing a faulty flame arrestor isn't urgent, or a cracked jar cover isn't urgent. Well, I beg to differ, because we've seen the picture of what happens, okay? If you have a cracked jar cover, okay, and there is hydrogen escaping out into the world, if somebody causes an electrostatic discharge on that jar and there is hydrogen available and there is a crack, not only will the hydrogen outside the cell combust, it will then get down through the crack of the battery into the space that has a huge amount of hydrogen, and you've just caused a bomb. Okay? And it will do this. It will blow that battery to pieces. And the same if the flame arrestor is broken. What you'll find is because flame arrestors push and twist in, sometimes the porous stone comes away from the bottom of the flame arrestor, and there's not a true connection anymore because the glue breaks. Once that happens, you must replace that flame arrestor immediately, or hydrogen will escape out and that flame arrestor will not prevent any ignition of gas out here to get back into the cell. So crack jars or flame arrestors that don't work are extremely dangerous and should be replaced immediately. Another battery myth. Oh, I like this one. Internal resistance checks, not the intercell resistance checks. Internal resistance checks on vented lead acid batteries are required. I've never heard so much nonsense in my life. Nowhere in IEEE 450, which is the recommended practice for maintaining vented lead acid batteries, does it even mention taking internal resistance or impedance in vented cells. Nowhere, absolutely nowhere. In the whole document, it does not mention it, okay? Because as long as you can see the plates in a vented lead acid battery, then you can visually see what's going on. You don't need to do internal resistance. Internal resistance is only used in valve regulated lead acid batteries because we can't see what the plates are doing. We can't see inside the battery. So somebody, basically Al Baer, came up with a way to kind of see what was going on inside the lead acid battery without being able to view the plates. And that's where internal resistance measurements came from. They are for valve regulated lead acid batteries only. Basically, it does nothing for a vented lead acid battery, because you'll see the plates degrade much quicker than with your eyes than with a cell coder or with a Midtronics, whatever device you're using. The only thing really that a Midtronics or a cell coder can do for vented lead acid batteries is see if there's a plate short or an open circuit cell, which is very rare. So internal resistance checks are not required or recommended on vented lead acid batteries. Another battery myth: I can't equalize VRLA batteries. I can't equalize valve-regulated lead-acid batteries. That's not true. It is manufacturer specific, and many manufacturers have strict guidelines on what their equalizing charges should be. Excuse me. And here's an example. So this is from a battery manufacturer's manual, and it says under normal conditions, an equalizing charge is not required. Okay, and then it goes on to say what an equalizing charge is. But mostly, the most important thing is this one down here. An equalizing charge should be given if the float voltage of any cell is less than 2.17 volts, or the float voltage range after 6 months of a cell is outside the plus or minus 0.8 volts. So let me explain that. So let's say the recommended float volt is 2.25 volts per cell. What they're saying here is if the cell voltage goes to 2.17 or to 2.35, sorry, 2.33, is it? 2.25 plus 2.33. If it goes out with that band, then you can do an equalize, okay? And then it goes on, then it tells you what that equalizing charge should be, okay? So every manufacturer has their own specifics for what equalizing their valve regulated battery should be. You cannot say a blanket, you do not equalize valve regulated lead acid batteries. I think this is the last battery myth. I can run my system without a battery connected. On a UPS, in most cases, that is true, although there are some older AMETEK UPSs that if you open the battery input breaker, it will shut the inverter off and transfer to bypass. But what's of more concern is for a DC system, whether it's for a switchgear system or something similar. Here is the standard drawing for a DC system, okay? This is how a full wave rectifier or a charger actually works. They take AC on the left-hand side and we turn it into DC on the right-hand side. Now, a lot of people would say that this is not DC, but it actually is. It's pulsating DC. We have just rectified everything above the 0 volt line, okay? The current is still moving only in one direction. So if you don't have a capacitor or a filter circuit on the output of the charger, this is actually the charge voltage that's going to your battery, okay? Now, when you put a battery on it, if you know anything about electricity or electronics, the battery has plates, a positive and a negative plate, and 2 plates separated by a dielectric, which is the separator, makes a capacitor. So a battery makes a capacitor. So if you connected this system to a battery, then the battery would fill in all these gaps here and would make it a nice DC. But as soon as you remove that battery, it would turn back into that pulsating DC. So if we have this one here is showing you what it should look like when you add a capacitor to the circuit. You can see here, this is pretty much flat DC. There's just a little bit of ripple on there, okay? So if you had an unfiltered charger and you opened the battery breaker here, okay, these load circuits here, whether they are trip and close supplies or auxiliary circuits connected to the DC, are going to be exposed to this, okay? And that is probably around about 170 volt peak if it's a 120 volt input system, 170 volt peak, and that does go down to 0 volts. So depending on what the tolerance of your loads are, relays could start chattering. That could cause serious issues. So that is why you should never open the battery breaker on a system if it has an unfiltered charger. Okay, and even in truth, on a switchgear system, you know, most charger manufacturers sell what's called a battery eliminator. Okay, which is basically saying that you can open this breaker here and all of your load circuits will work okay. They will work okay, except for when somebody sends a trip or a close signal to one of these breakers. And when that happens, the current required to charge that spring may be above the value of what that charger can supply. And that will cause a dip in the DC voltage, which could cause issues on other load circuits. So best practice is, if you are ever going to remove your battery from service, you should tie in a temporary battery. So you have a temporary battery in here that's supplying power, and you're never left just relying on the charger. Okay, and as usual, I'm 5 minutes over time because I speak too much. So let's go to the chat bar. Okay, and see if we have any questions. And if you have any questions, please let me know. So, what are the normal electrolyte levels pre-charge, during charge, and after charge? Okay, that's a good question, Sol. And I can't tell you what the levels should actually be, but what people don't realize is when a battery is discharged is some of the acid, in fact, quite a lot of the acid has been absorbed into the negative plate. So the electrolyte level will naturally go down when the system when the battery has been discharged. And not only that, there are some bubbles within the electrolyte, like when you put a battery back on charge, there are some bubbles which will cause the overall surface area, I suppose, of the electrolyte to go up. So it's a difficult question to answer. But what I would say, Sol, is always make sure you're only checking electrolyte levels when the battery is fully charged. That is the only thing that you need to concern yourself about. And that's especially true when you get a brand new battery from the manufacturer. In most cases, a brand new battery from the manufacturer will have low electrolyte levels. And it's only when you put that battery back on charge that the electrolyte levels will go back up to their nominal, pretty much halfway between the minimum and maximum line. Okay. Frederick, are we going to receive recordings of this webinar? You will receive a link, and we are putting it on our YouTube site tomorrow. So, yes. IEEE 450 210 Annex J shows using internal ohmic readings as an alternative inspection means. I thought I looked at the latest version. Maybe I didn't look at the annex. I would still say that near enough everybody in the battery maintenance world agrees that internal ohmic measurements of a wet cell battery gives you very, very little information compared to the amount of time and the expense that is required to do that maintenance. There are much better, simpler, less costly ways to check the internals of a wet cell battery where you can see the plates. Let me go into the Q&A and see what's in there. Do VLA and VRLA products off gas? Absolutely, yes, they do. Valve regulated batteries, not as much as vented lead acid, but for vented lead acids, all the battery manufacturers will stipulate how much hydrogen is off gassed. And similarly for VRLA as well. But for VRLA, the recombination valve on those batteries is supposed to reduce the off-gassing to a very minimal amount, which tends to allow them to be put in rooms where vented lead acid batteries can't be put. And there's actually there's a gentleman on this webinar, I think his name is Peter, contacted me. You can actually get recombination valves or flame arresters basically for vented lead acid batteries now, which reduce the off-gassing and reduce the amount that you need to top up the battery's electrolyte. Basically, it turns a vented lead acid battery into a valve regulated lead acid battery. So they are available. So yes, both batteries off gas, but VLA batteries much more than VRLA. What is the main difference between float and equalized charging modes? Float mode is what you should be charging the batteries at a consistent level. So for the whole life of the batteries, the float voltage is what you should be charging your batteries at. And it's only when, as per the manufacturer's guidelines, some of your cells go out of tolerance. So if we go back to the Enesis, where it said, I think it was for a specific cell, they said the charge voltage should be between 2.18 and 2.25 volts per cell. So they're saying that you should charge that at roughly 2.23 volts per cell, but they're saying if a cell is found below 2.18 or above 2.25, then that is when you need to perform an equalize on the battery string. Because what an equalize does is basically overcharge the batteries so that any undercharged batteries in that string come back up to a fully charged level. And then when you remove that overcharged voltage and current, then everything else should have equalized back to normal. That's what an equalize means. So you shouldn't, a lot of people have in their PMs that you should equalize your batteries every 6 months or equalize your batteries every 3 months. That's not what you need to do. What you need to do is follow the battery manufacturer's guidelines, and only if cells are out with the tolerances that the battery manufacturer stipulates, then you perform an equalize. And the equalize has to be done as per the manufacturer's guidelines as well, which means most manufacturers for vented lead acids would say equalize your batteries at 2.33 volts per cell. And they'll say usually for a 72-hour period. But that 72-hour period doesn't start until the current going into the batteries has stabilized for a prolonged period of time. So when you press the equalize button, the float voltage of the charger is going to be increased to around about 140 volts DC for a 60-cell system, which is going to drive more current into the battery. So what you need to do is you need to get an amp clamp, and you need to monitor the current going into the battery, and you need to check that current every hour. And when you have 2 readings over the space of an hour that are the same, then you can say that the current has stabilized, and therefore you can start the 72-hour equalize timer. If you don't wait for the current to stabilize, especially on big batteries, then you are not performing a correct equalize of the battery, and the cells will go out of tolerance very quickly again. A question from Nick: how can we know if the flame arrestor is faulty? Really, it's mechanical. If the flame arrestor falls apart in your hand and it's not mechanically sound, then it's not good. Also, there is a rubber seal on the bottom of the flame arrestor, and that creates a seal between the jar cover and the flame arrestor itself. That needs to be in place. So that's really the 2 mechanical things that you can check. And in truth, read the battery manufacturer's guidelines. They also say that the flame arrestors should be cleaned once in a while, especially if you notice that on the porous stone starts to get discolored, then you should rinse out the flame arrestors as per the manufacturer's guidelines. But really the 2 ways to know that a flame arrestor is faulty is mechanical. Whether the porous stone has come away from the flame arrestor tube itself, or whether the seal on the bottom of the flame arrestor is bad. Okay. That's really the two ways that you can find out. Did I miss you talking about temperature and its effect on battery life? Yes, you did, Ben. How dare you? I accept your apologies. I did talk about temperature and its effect on battery life. So you can go back and watch the YouTube video all over again. It doesn't look like there has been any more questions. So I will say that if you do have any more questions, then you can reach out to AMETEK Solidstate Controls via our website. London will put a link into the chat bar here. It will give you the email address or the contact form that you can fill out to get in touch with us. Also, don't forget that we will be putting the full video on our YouTube channel tomorrow, and London's going to put the link in there for that. Oh yeah, and you can also contact us by telephone. We still answer telephones, believe it or not. Crazy, I know. But you can call us up and a human will answer it. You do have to go through a couple of menus, but you will get to a human usually. And you will be sent out a survey after this. And I do read every survey. I'm not looking for compliments, believe me, and I don't delete surveys that say that I'm terrible. What I'm actually looking for is what topics that you want to see for future webinars. So if you have a really good topic that you would want me to discuss at our next webinar, please fill out the survey. I think it's question 5, which topics you would like to see in the future. I read every single one of those, and that's how I compile all of my webinars. So please do fill that out and let me know what you want to see. Goodness me, that's an hour and 15 minutes. What I would like to say is that's an hour and 15 minutes of your time. I really, truly appreciate you spending that time with us. The one Wednesday every month that we do these webinars. I know everybody is very, very busy. And for you to spend that time with us, we don't take that lightly. We really appreciate that. So without any more questions, I'd like to say thank you once again. Take care until our next webinar. That might not go ahead in November. Obviously, it's going to be Thanksgiving. So pay attention to your emails. We may skip next month's webinar, but we'll see how it goes. But once again, thank you and take care until next time.